Good day, grade 12 learners and teachers. Welcome to today's mathematics lesson. I'm Mr. Shongwe, and this lesson is brought to you by the Gauteng Department of Education in collaboration with Bono Discovery Center. Right, good people, today we are looking at interpretation of sketched functions. But remember, in order for you to be able to interpret sketched functions, you should go back to grade 11 and look at sketching, look at the basic characteristics of functions, your x-intercepts, your y-intercepts, your asymptotes, your axis of symmetry, your turning points. All those characteristics that are unique to specific functions need to be known. And then that you can be able to then go into aspects of interpretation. So I'll be looking at those aspects with you today of interpretation. To start off, let's look at the lesson objectives. We need to, by the end of the lesson, you need to know how to determine the equation of a sketched function, to identify and calculate the x and y intercept using the Joule intercept method, to calculate the horizontal length, the vertical length, the diagonal length, as well as extend that knowledge to maximum and minimum length, apply transformation in the context of functions, solve inequality problems by graphical approach only, solve problems that involve nature of roots using graphical approach only. Right, obviously, you can refer to the policy document on page 32 as well as the exam guideline on page 6 to see the scope within which you should know your functions. Right, pre-knowledge that you need. Sketching, as I indicated when I started the lesson, you need to know how to sketch a straight line, a parabola, a hyperbola, and an exponential function with one or more parameters using the dual intercept method. Right. The functions that you should know are of this particular form. But with this parabolic function, you can also extend the standard form to ax squared plus bx plus c, like that. So also the effect of parameters a, q, and p on all the functions mentioned above should be understood. Determine the domain and the range of all the functions as well. Straight line, a parabola, a hyperbola, and an exponential function. Right, determining the equation now. Let's look at the equation of a sketched function. To start off, we are going to look at the parabola. Now, when determining the equation of a parabola, there can be two different forms. When you are given two x-intercepts and a point, then you are to use y is equals to, you are to use y if you are given two x-intercepts and a point, you should use y is equals to a into x minus x1 multiplied by x minus x2, where x1 and x2 represent those x-intercepts, and then you will substitute the point to get the value of a. But when you are given a turning point and a point, if you are given a turning point and a point, then we have to revert to y is equals to a into x plus p squared plus q. You will take the turning point form of the parabola. But if you are given two x-intercepts, you will take the dual intercept form of the parabola. Right, let's look at this one. If you check here, you are given the x-intercept -5, you are given the x-intercept 1, and you are given a y-intercept, which is the additional point. So because you are given two x-intercepts, so these are x-intercepts, you are going to be using the dual intercept form. So let's look at that now. Obviously, I indicated you should be using y is equals to a into x minus x1 x minus x2. You can see we've substituted x1 as negative 5, so it would be, you would have that this would be a into x minus negative 5, close bracket, x minus 1. So that is where we got the positive 5 there. Then we need to substitute the additional point at a point 0 and minus 5. This is the additional point there. When we substitute a point 0 and minus 5, so where we see y, we put negative 5. Where we see x, we put 0. And then from there, we can open those brackets. From there, we can open those brackets. We multiply 0 plus 5 is 5. 5 multiplied by negative 1 is negative 5. And then negative 5 is equal to negative 5a. And then dividing both sides by negative 5 yields a is equal to 1. Now that you have the value of a, you will go back here and substitute the value of a so that you can be able to then apply the distributive property and be able to write the equation in the required form. So now we substitute 1 there, and then from there we apply the distributive property where we are going to multiply inside like that. And then from there, we got that y is equals to x squared plus 4x minus 5. So we have managed to actually determine the equation of that particular parabola. Right, we move on to the next one. Now, if you look at this one, we are now given the turning point, and we are given the additional point there. So if we are given the turning point and the point, remember I said we will revert to y is equals to a into x plus p squared plus q. That is the turning point form, where negative p and q represent the coordinates of the turning point. In this case, the coordinates are given, so we're going to substitute here negative 1 and 6 into that particular equation. Let's see. There we go, because we see that we are given negative 1 and q, so which means that the turning point is negative 1 and 6. So it means that p is 1 and q is negative 6. So we substitute there p as negative 1, so we get that this would be 1 squared, and then we get that this would be plus 6. Then from there, we can substitute the additional point 0 and 2. That y-intercept 0 and 2. Where we see y, we put 2. Where we see x, we put 0 there. And then from there, we are going to simplify here. 0 plus 1 is 1. When you square 1, you are going to get 1. And then from there, multiplied by a, so it would be a plus 6. And then from there, we will transpose the 6. 2 minus 6, we get that a is negative 4. Now that you have the value of a, you can come back and substitute the value there. If you substitute the value there, and then from there, you can apply distributive property here and FOIL out the bracket x plus 1 all squared to be x squared plus 2x plus 1. After FOILing that out, you can then apply the distributive law, because there's a 4 there. You distribute the 4. So that's what we can do here. We started by opening up that bracket, and then from there we distributed the 4 and we added 6, because if you distribute the 4 there, you'd get negative 4x squared minus 8x minus 4 plus the 6, this 6 there, that would then give you positive 2. So you were successful in writing down this as negative 4x squared minus 8x plus 2. That would be the equation of that particular parabola there. Now, I want us to go slightly back, and I want to explain that particular concept. I want to explain the concept that we are busy with. that would be determining the turning point of that particular equation there. Right. If we want to determine the equation of a parabola, first we need to check what is given. If we are given a turning point and a point, then we are going to use the turning point form. Y is equals to x plus p all squared plus q. And then if we are given two x-intercepts, then we need to use the x-intercept form. Y is equals to a into x minus x1 multiplied by x minus x2. So you need to check which form is given. Right. So now we move on. We move on now to another function. In this case, it's a hyperbolic function. We are given the asymptotes x equals 1, y equals 1 as well, and then we are given the additional point. So here you just need the asymptote and a point. So we are given both the asymptotes and we are given a point. So our interest is calculating the value of a, because once we have the value of a and we have our asymptotes, then we would have the equation of a hyperbola. Right, let's look at it now. Checking this out, the first things first, we substitute the asymptotes because we are given that x is equals to 1 and y is equals to 1. So we are going to substitute because we know x is the same as p in this case, which is 1, and then we have that y is the same as q there. So we've replaced p with 1 and we've replaced q with 1 as well there. So now that we've substituted that, we will then substitute a point at a point 3 and 2. So where we see x, we put 3. Where we see y, we substitute 2. So now we have 2 is equals to a divided by 3 minus 1 plus 1. And then we simplify that, we get that 3 minus 1 is 2. We transpose this one this side, so 2 minus 1 will give us 1 there. So simplifying this further, we get that a equals 2. And then from there, we can go back here where we see a, we put 2, and that would complete the equation. There we go. Y is equals to 2 divided by x minus 1 plus 1. So that is how you determine the equation of a hyperbola. You need the asymptotes and an additional point. And fortunately, in this particular question, you were given both the asymptotes and the point. And then from there, let's move on to the exponential function. For the exponential function, we are given this form, and we are given the asymptote. Remember, y is equals to 2, and that is the horizontal asymptote q. So we are given the horizontal asymptote q, which tells us how much the graph has shifted up. And then from there, we will need the value of p, which means that we will substitute the additional point. Where we see x, we put 1. Where we see y, we put 6. And then we'll solve for p. Now, let's see. To start off there, I substituted the vertical shift, the value of q, as 2, and then from there I will have to substitute x and y from the given point and solve for p. The given point is 1 and 6. Where I see x, I substitute 1. Where I see y, I substitute 6. And then from there, I solve. Transposing the 2, I get that 6 minus 2 gives me 4. And then I'm left with 2 to the exponent of 1 plus p. We know that now we can write this as prime basis. 4 can be written as a base of 2, and that would be 2 squared. So we write 4 as 2 squared, and then we have 2 to the exponent of 1 plus p, and we apply the laws of exponents now. If the bases are the same, then we can equate the exponents. So we have that 2 my 2 would be equals to 1 plus p. We are equating the exponents, solving for p by transposing 1. We get that p is 1. Then we can come back here and substitute 1 where we see p, and that would conclude the equation of the hyperbola, or of the exponential function. Sorry, it's the equation of that given exponential function there. Right, let's move on. I hope you are still following, because that's the first step of interpreting functions, is to be able to go back and determine their respective equations. Right, we move on. Now we look at the concept of intercepts, distances, as well as the gradient. Let's start x-intercept. We know to determine the x-intercept, we substitute y with 0 and we solve for x. The y-intercept, we substitute x with 0 and we solve for y. Now, most important, when we want the horizontal distance, remember the horizontal distance is this particular distance here, where y is equals to 0. We are talking about the distance that is parallel to the x-axis. So if this was point A and this was point B, x at A, y at A, x at B, and y at B. To determine the horizontal distance, we'll take x on the right minus x on the left, which means that the distance AB would be equals to x at B minus x at A, because x at B is on the right hand side, minus x at B. Y does not change. We are looking for a distance of a line that is parallel to the x-axis. Now, let's look at the vertical distance. The vertical distance, we are talking to the distance that is parallel to the y-axis. So that would be a PQ. That would be x at P, y at, or at Q, y at Q, x at P, y at P. If we want to determine the distance PQ, we are always going to take y value at the top minus y value at the bottom. Y top is y at Q minus y at P. So that's how you can determine the distance of a line that is parallel to the y-axis. And then from there, if you want a diagonal distance, that would be a line that is not parallel to the x-axis and not parallel to the y-axis. It forms an angle with the x-axis. So that line would be a diagonal line. If you want to determine its distance, then you can make use of the distance formula. This is called now the distance formula. You know it very well from analytical geometry. Right, and then if you want the distance between two graphs, it is always the top graph minus the bottom graph. That is why I took f of x minus g of x, where f is above g. And then from there, the average gradient is y2 minus y1 over x2 minus x1. In functional notation, it's f of x2 minus f of x1 divided by x2 minus x1. So that is the theory. Let's then move on. And now, in order for us to check whether you understood that theory, you have to be able to respond to questions here. So I am going to actually give you these questions, and I would request that you answer them in 8 minutes. This can be 4 marks, and then this can be 2 marks, and then this can be 2 marks as well, and this one can also be 2 marks. So I want you to try to respond to those questions to the best of your ability. I would give you 8 minutes. Please be as quick as you can, and your 8 minutes time starts now. Right, hello and welcome back. I hope you enjoyed this little problem here that you were supposed to solve. Not too complex, but it is testing the skill set of the table here. Because remember, I was explaining concepts in the table, so we are just looking at extending that to you so that you check your skill set there, and this should be revision of grade 11 concepts. Right, let's look at the length of AB. Look at A and B. You can see that A and B are both x-intercepts. Because they are x-intercepts, we need to first determine the x-intercept by putting y to be equals to 0 and then solve for x. Then we locate the points there before we can ultimately work out the length, because we are looking at this length and this length is parallel to the x-axis. It is a horizontal length, right? Now, that is the equation of the function. Then you can see that we are putting y to be equal to 0 because these are x-intercepts. So x-intercepts, these are x-intercepts. We let y to be equal to 0. So if we let y to be equal to 0, then you see here that we are able to solve for x because y is equal to 0. We are able to solve for the x value there. Now, in solving that, we can actually find the factors there. The factors of 10, that would be 5 and 2. Those are the factors that would give us 3. And then from there, in solving for x, we get that x equals -5 and x equals 2. And we can see that the value of a is negative, so it is we are going to choose the -5 there, and the value of b is positive. It's on the positive axis, so we're going to choose 2 there. And then the horizontal distance then should be x on the right, that's x at b minus x at a. So the horizontal distance, that should be the distance of AB, that should be x at b minus x at a, like that. So if we check there, x at b in this case would be 2 minus -5, and that would be 2 plus 5, which would be 7 units. So that is why we get 7 units there. So to distribute the 4 marks, we are going to mark the fact that you determine the x-intercept by making y to be 0, and then from there we're going to mark the factors. We're going to mark both terms, and we're going to mark the length. So that is where the 4 marks would be coming from there. Right, now let's look at the length of OC, the second one, the length of OC. OC, you can see that OC is the vertical distance. OC is the vertical distance. And to work out OC, we need to then look at point C. Point C, you can see that this is the y-intercept. So to determine the y-intercept, we're going to say point C is the y-intercept. And to determine the y-intercept, I'm going to put let x to be equals to 0. So where I see x, I put 0, and then where I see y, I am going to then what you call solve for y. Where I see x, I put 0, and then I solve for y. And if I know the y value there, then I can be able to determine the length of OC, because it is the vertical length. So let's see here. We can actually let y to be equals to 0 in any of these equations, because point C is the common y-intercept. It is the y-intercept for the straight line and y-intercept also for the parabola. So I can substitute in any of the two. In this case, I chose to substitute 0 on G. So I get that y is equals to 10 there. So I will then need to take the distance OC as y top minus y bottom. Y value at the top is 10 minus Y value at the bottom is 0. So this gives us 10 units. So in doing that, you see OC is 10 units. That would be for 2 marks. How are you going to get the 2 marks? Substituting y as x as 0 to get y, and then the length there 10 units. So that would give you your 2 marks there. Right, let's move on. The length of AC, you can see that now AC is a diagonal length. So to determine a diagonal length, we must use the distance formula. You must use the distance formula. In this case, you can also make use of the Pythagoras theorem. It can work because this triangle here is a right angle triangle. So you can use Pythagoras to work out the length of AC, but in any other case, you would be using the distance formula. So you see, there is my distance formula. AC is the square root of the x at C minus x at A squared plus y at C minus y at A squared. So if we substitute those values, remember we have the coordinates of A, we've determined that as -5 and 0. We determine the coordinates of C as 0 and 10, like that. So we substitute those values there, and then from there we get that AC is 5 square root 5. That would be the length of AC. For 2 marks, substitution and an answer, you get your 2 marks there. Right, then let's look at the area of triangle AOC. The area of this particular triangle here that I'm shading, obviously it should be the area, because this triangle is a right angle triangle, is half times the base. The base is OA multiplied by the perpendicular height, which is OC. So we need the length of OA and the length of OC, and I think we've already worked out those lengths. OA, we did not work it out. That would be this length, but you can see that OA is x on the right minus x on the left. It's 0 minus -5, so OA would be 5 units. We know OC, we've worked it out as 10 units. So in order for us to simplify that, let's check now. It's half OA, which is 5. That would be OA, which is 5 units, and then this would be OC, which is 10 units. So to simplify that, we get that the area is 25 square units. So the area of that triangle is 25 square units. So for that substitution and answer, you get your 2 marks. So that would conclude the problem that we had to actually solve there. Right. I think we are still on par. You are still okay. Let's get to move on. Remember, if you have questions on what we are busy with here, and there are things that you do not understand, please make sure that you ask on our WhatsApp line. It is active at 064 748 8913. 064 748 8913. I think it's there also at the bottom of your screen. You can actually ask those questions about the lesson that we are having right now. We will be able to respond to your questions. Right, let's move on to graphical transformations. Let's look at the concept of graphical transformations now. In functions, when we look at the concept of transformation, we are going to be looking at 2 different concepts in this case. We are going to be looking at translation, that would be the change in position, movement up, movement down, that would be translation, movement to the right, movement to the left, that would be transformation. Translation as the first type of transformation. And then we'll also look at the reflection, which is the change in orientation, where you are going to reflect about the x-axis or about the line y is equals to 0, and then we also reflect about the y-axis, that would be the line x is equals to 0. So those are the type of transformations we'll look at, and we also look at the horizontal stretch and the horizontal stretch as well as the vertical stretch that is governed by the value of A there. Right, let's look now at the first type of transformation. That would be translation. We start with the vertical shift. That is movement of the graph up or down. That is the vertical shift. Now, vertical shift only affects the y values because the graph moves vertically up or down. It does not move horizontally, so it moves parallel to the y-axis. So then you see that here, if you had the coordinate x map y, then that coordinate x will remain because x is not affected, but y will then be shifted by q units either up or down. So we say that the graph shifts up when q is positive and the graph shifts down when q is negative. So the shift is in accordance with the value of q and the sign of q. When q is positive, shifts up. When q is negative, shifts down. And then let's look at the horizontal shift. The horizontal shift is movement to the right and movement to the left. So that particular shift would be governed by the value of x because the graph is now moving with respect to the x-axis. So if you had a point x and y, then that particular point would be given by x plus p as well as y. So the parameter p is added to the value of x because there is horizontal movement. The value of y remains as is, right? And then from there we can see that if p is positive, the graph shifts to the left. If p is negative, the graph shifts to the right. So the graph is shifting opposite to the value or the sign of the value of p. That is what we should note there. And then also let's look at the function notation. The function notation is if you had a function f of x and you are reflecting or you are translating f by q units, then the new function g of x would be governed by what? F of x plus what? Plus q, because you are forming a new function by transforming the old function. So you get that the new function g, if g represents the new function, it would be f of x plus q. And then from there, obviously, let's look at the function notation here. If you had a function f, of x and you are shifting f of x by p units horizontally, then a new function g that is formed, it would be f reflected or f translated, I should say, by p units. So that would be the relationship between g and f, if g represents the new function that is transformed. Right, let's look at now, before that, we should be looking at, that is the example there. We should be looking at that particular example there. Right, let's go to that example and let's quickly work on that particular example. But first, I would just need us to just take a 1 minute break before we get to that particular example. Just a 1 minute break just to stretch our legs before we look at that transformation. So the 1 minute break starts now.
Do you know that you are different? Do you know that your fingerprint is different? Is different from your peers, from the people that you are studying with. So do not compare yourself with your peers. Do not compare your results with what they're getting, because you are different. You have your own talents and skills, and also you have your own gifts. Embrace what you can do. Always put in the work to make sure that your results become better than what they were yesterday. But do not compare yourself, because when you compare yourself, you do not know what another person has, and they do not have what you have. So believe in yourself. You are different, and keep on putting the work.
Right, hello and welcome back. We looked at the first type of transformation. In this case, we're looking at translation. And I said there are two types. This would be type 1. There are two types. The second one would be reflection. So we're supposed to also look into reflection. And then we also talk about the third one here, which is just a horizontal stretch of the graph there, right? Or squashing or stretching the graph horizontally there, right? Let's look at reflection in the x-axis. When we reflect about the x-axis, then y becomes negative, which means if we have a point x and y, then this point would be x and negative y. So when you reflect about the x-axis, y becomes what? Negative y. That is very, very important. And then in the function notation, remember in the function notation, y is f of x. So that is why we put a negative there on f of x, because y becomes negative. So the graph would flip about what? The x-axis. So the graph would be flipping about the x-axis. If it was on the positive x-axis, it would be on the negative x-axis. It just flips about the x-axis, right? Let's look at the reflection in the y-axis. Y-axis, we then x becomes negative x. So the axis that you are reflecting with maintains its sign, and then the other axis changes the sign. X-axis, y changes sign. Y-axis, x changes sign. So we get that now in the function notation where there was x, we are going to replace it with negative x. So the graph flips about what? About the y-axis. So the graph is going to flip about the y-axis, which means that if the graph was on the left-hand side of the y-axis or the right-hand side of the y-axis, the graph will then now be on the left-hand side of the y-axis. And then we are talking about the vertical stretch. For the horizontal stretch, we are talking about changing the shape of the graph. So now the graph stretches away from the x-axis when a is greater than 1 and when a is less than -1. So it stretches away from the x-axis there like that. So the graph stretches towards the x-axis when a is trapped between -1 and 1, then it leans closer and closer to the x-axis when that happens, right? And then let's look at now the example now. We've spoken about reflection, translation, horizontal translation, vertical translation. We've spoken about reflection in the x-axis, in the y-axis. We've spoken about the squashing or the stretching of the function when you have a factor of a there. Now, write down the equation of the resulting function when the function is reflected about the x-axis. At times, they will say it is reflected about the line y is equals to 0. So you need to be careful. If they don't say the x-axis, they can say about the line y is equals to 0. So that's very, very important there. Right, if it's then if the function is reflected about the y-axis, that is x is equals to 0. If it's shifted 2 units up and 1 unit, or 2 units to the left and 1 unit down. So this the third one is a translation. The first two represent a reflection. Now let's check. I indicated to you that when we are reflecting the graph about the x-axis, what happens? Y becomes what? -y. So you can see here the original y that was there, I replaced it with -y, and then I make y the subject of the equation there by dividing both sides by negative or multiplying both sides by -1. Applying the distributive property, I get the new equation to be y is equals to 3 over x minus 2 minus 3. And then second one, it is reflected about the y-axis. If it is reflected about the y-axis, it means that it's reflected about the line x is equals to 0. So where we see x, we're going to put negative x. So you can see here, we've replaced the x with negative x. And then from there, continuing with that, we get that if we can take out a negative sign here, we'll get that this is y. This would be y is equals to, let me write it here. If we take out a negative sign, y would be, y is negative 3 over negative into x plus 2 plus 3. And then from there, we divide the two negatives to get the 3 to be positive, right? Last but not least, you are reflecting, it is shifted 2 units to the left and 1 unit down. 2 units to the left and 1 unit down. If they say to the left, then it means that you are moving towards this direction, 2 units to the left, which means x is equals to negative 2, which means that you, if you transpose that to get the transformation would be x plus 2. That is why we replaced x with what? X plus 2. And then 1 unit down, downwards would be in this direction, which means that y would be negative 1, q would be negative 1 there. So where we have the y value there, the value of q, we are going to then move that value by 1 unit down. So simplifying that, we get that this is negative 3 over x plus 2. So that would be the solution set for that, right? Now I have an activity for you to do. I will give you 5 minutes to work quickly with that activity. 5 minutes just to work with those transformations, and your 5 minutes time starts now. Right, hello and welcome back. Hopefully you were able to exert yourself in those problems that we were trying to solve there. Just want us to quickly go through the solution set that you're supposed to actually have. Just check with your work and what I'll be doing here and quickly mark your work. Right, given f of x is 2 to the exponent of x minus 1, if g of x is f of x minus 1 plus 2, determine the equation of g and describe the transformation from f to g in weight. Right, first things first, we need to determine the equation of g using this translation. You can see that there's a movement there, horizontal and vertical movement. So let's determine the equation. So we are going to, where we see in the equation of f, where we see x, we're going to put x minus 1, and where we see a constant there, we're going to add 2 there. Right, let's see. There we go. Where we see x, we put in x minus 1, and then we added 2 to the whole thing. And then from there, when we simplify, we get that g of x is 2 to the x minus 1 plus 1. That is the equation of g. And then now we need to describe the transformation. You can see that from f to g, this is x minus 1 is 0. So we can see that x is equals to 1, which means that we moved 1 unit to the right, and then also plus 2, which shows that y is equals to 2. It means that we moved 2 units upwards. So that is the description there. F is shifted 1 unit to the right and 2 units up to produce G. F is shifted 1 unit to the right and 2 units up to produce G. Right, that is the first type of equation. The second one, determine the coordinates of the turning point of G of x if g of x is f of x plus 2 minus 3. So now you can use two methods here. The first method would be to write down the turning point of the original function f, and then you apply the transformation that you see here. This is the transformation. The transformation is x plus 2 is equals to 0. X is negative 2, and then y is negative 3. That is the transformation, which means that you'll take a point on the original turning point. On x, you subtract 2. On y, you subtract 3. That is the first method you can use. Another method would be to write down the equation of the new function g. Writing down the new equation, and then after that you determine the new turning point from the new equation. So it's either we are going to write the original turning point and we apply the transformation to it, or we write down the new equation, transformed equation, and then we determine the turning point from it. So let's check the one that I used here. I used the turning point of f. I wrote down the original turning point here. That is x minus 1 is 0. X is equals to 1. So we are turning at x is 1 and y is 2. That is the value of q. So that is the original turning point. Now, what is the transformation? I indicated the transformation here. From x, you subtract 2. To get the turning point of G, what are we going to do? We are going to take from x, we subtract 2, and then from y, we subtract 3. So if we do that, we get negative 1 and negative 1. That is the new turning point. Alternatively, we might have to change the equation and say the new equation for G, that would be the alternative method. Where we see x in the original, we are going to replace it with x plus 2 and then minus 1 squared, and then we're going to then subtract 3 from that. So we get that the equation of G would be x plus 1 squared minus 1. So the new turning point, the turning point for G would be -1 and -1. So you can see we get the same solution, but we are using the different method, right? I'm moving on to the third one. Last but not least, we are given the hyperbolic function of this nature. We want to determine the range of R of x, which is f of x minus 4. Remember, if we want that range, there are two methods. We can determine the original range, the range of G, and then we check what the transformation is. We apply the transformation to the range of G to determine the range of R, because G was transformed to form R. Second method, you can actually take the equation, write down the equation of R first, and then determine the range from the equation, right? The one that I adopted here is the latter method. The range of the original function is y, an element of all real numbers, but y cannot be 3. And then now we apply the transformation. What is the transformation? X minus 4 is 0, x is equals to 4. So we have that the graph is moved by 4 units to the right. So moving the graph 4 units to the right, let's see what will happen to the range of R. It should be R. The new function is R. The range of R would be the same as the range of F. Why is that? Because the movement was only to the left, so the range was not affected, only the domain was affected. Alternatively, you can determine the equation of R to say R of x would be f of x minus 4. So where we see x, we're going to put x minus 4. So this is x minus 4 plus 2 minus 3. So this would be -6 is x minus 2 minus 3. So you can see that the range here would still be the same. The range would be preserved. It will not change because the y values would not change. So the range would be y, element of all real numbers. Y cannot be -3. So the range would be preserved there. The range will not change. Only the domain will change because we are moving with respect to the x-axis, or we are translating horizontally. Right, let's look at the concept of inequalities in the graphical application there. Let's look at inequalities there. Now, let's check. The first thing that you need to know is the notation. If we are using a round bracket, so we are saying that the round bracket together with the less than, which is not included, or an open interval, represent values that are excluded. But if you are using the square bracket there and you are attaching that line there to the inequality and you are shading that particular oval there, it means that the values are included. And then from there, you can see here the first value is included. We can represent it here as well with the inequality, the bound inequalities. Maybe for y, the first value is included, is not included, but the second value is included, like that, if you are putting in different values there. So you can see that the first value is excluded and the last value is included, and then because of the restriction that is there. And then here values are excluded because of the restriction that is there, and then values are included in that one. Right, we move on. Now we look at the solitary functions. If they are saying to you, where is f of x greater than 0? They want the values of x where the graph of f is above the horizontal. Let's say, for an example, this is f. So they are looking for the portion. You see, this is the x-axis. So they are looking at a portion of the graph which is above the x-axis. So we are focusing on this portion, the portion that is above the x-axis. And here they are talking to where f is below the x-axis. So we are looking at the portion that is below the x-axis. F of x equals 0. We are looking at directly the x-axis. That means that we are looking at the x-intercept. Right, let's move on to the comparison. So here it's not the solitary functions, it is the comparisons. So there's a typing error there. It's comparison. So if you look at comparisons now, you are comparing two functions. You are no longer working with one function. If you check here on solitary functions, we were just working with one function. It was f only, but now g comes to visit. Now when g visits, it's either we can compare both f and g, or we can combine. Now let's look at the comparison first. When f is equals to g, that is the point of intersection, f of x equals g of x. But now when f is greater than g of x, you are looking at the region where the graph of f is above, is on top, and then the graph of g is below. So when f is less than g, you are looking at f now is below g, or g is above f. And then there is a special case here, f of x minus g of x is equals to -1. We are looking at a region now where f is above g, right? F is above g, and the distance between f and g is 1 unit. So f, because comes first, f is above g, and then the one here says distance is equals to 1 unit. So that's what you're going to be looking at. Remember, sometimes they can say f of x less than g minus g of x is less than 0. This is the same thing as the second one here. It's the same thing as this one, because you are now, this one I mean, you are now going to just transpose, because this value is 0, so you get that f of x is less than g of x. But if there's a number there, then you have a problem. You cannot just transpose there. Right, we move on. Now we are looking at here, these are not solitary functions, these are now we are talking now combinations. No longer solitary functions. Solitary functions, we looked at it there, so it's just a typing error. We are looking at combinations. I said to you, when you have two functions, you can either compare them where the other one is above or below, or they are equal, or you can combine them. When you combine, it's either you multiply the first function with the second, or you divide the two. That is combining them. So this one, if they say f of x times g of x is 0, you are looking for the x-intercept of both f and g, because this is when f of x is equals to 0, or g of x is equals to 0. What is f of x equals to 0? That is the x-intercept. What is g of x equals to 0? That is the x-intercept of g as well. So f times g of x, which is 0, represents the x-intercept of both the functions. And then the product, this means that now where both graphs are above the x-axis, or both graphs are below the x-axis. And then that is when the product is positive. When the product is negative, one graph is above and the other is below. So the explanation here is the same because of division. However, you need to note that here there's a restriction, because it's a fraction and the denominator cannot be equals to 0. So that is where the restriction would be. And then from there, x times f of x, we are saying the positive x-axis and the graph of f above the x-axis, or the negative x-axis and the graph of f below. Similarly, when x times f of x is less than 0, we are looking at the positive x-axis and the graph of f below the x-axis, or the negative x-axis and the graph of f above the x-axis. So that is the explanation of the inequalities. Right, now I will give you an activity where you apply this explanation that I've just provided. So I have a short activity for you where you can just apply the knowledge of the inequalities in the context of functions. Remember, we are only reading off the answers from the graph. We are not going to perform any algebraic work. So I am giving you 5 minutes to quickly look at these questions. Your 5 minutes time starts now. Right, welcome back once more. Let's look at how you were supposed to actually solve this particular question here. Inequalities, when the functions f of x is negative 2x minus 8 and g of x is negative 2x squared minus 8, given those functions, determine graphically the values of x for which f of x is greater than or equals to 0. So we are looking at a region where f is above the x-axis, where f is above the x-axis. Now, when you check the graph of f, you can see that there's a portion here. There's a portion there, this particular portion, which is above the x-axis. So we want that. So that would be when x is less than or equals to -4. There we go. It's this side. When x is less than or equals to -4, you can see the graph is above the x-axis. Right, where f of x equals g of x, this is the point of intersection. What are the values of x at the point of intersection? X is -4, they intersect here. X is 1, they intersect there. So those are the values we are interested in. X is -4 and x is 1. So you get this, and that. And then from there, f of x is less than g of x. So you are looking at a region where f is below g. F is below g, and f is a straight line. So the straight line is below here. If you check between the points of intersection, you can see that the straight line is below. If you look at this graph, you can see the straight line is below and the parabola is above. So the parabola here is above and the straight line is below. So that would be in between the turning or the points of intersection, I should say. So you get a mark for that. And then we have g minus f is equals to 8. So g is above f and distance is 8 units. G is above f and the distance between them is 8 units. Now let's see, where can that be? Now if you check, let's locate the y-intercept of the straight line. The y-intercept of the straight line would be -8 because that's where x is equals to 0. So it would be -8 and you have 0 here. If you are to check this distance, you can see that this distance here is y top minus y bottom, 0 minus -8, which is 8 units. 8 units. So we are looking for that. The distance is 8 units. So where f, g is above, the parabola is above, the straight line is below, the distance is 8. That occurs when x is equals to 0 there. That's why we get x is 0 here. Last but not least, f times g is negative. So in this one, we are going to actually try locating that region. F times g, we know. F times g is equals to 0. We are combining, so we need to focus on the x intercept. So we're going to focus on this x-intercept here. We are also going to focus here on this x-intercept. So we are going to be focusing on -4 as well as 0. Those are the x-intercept of interest that we are going to be focusing on. Let's see Yeah, those are the x-intercepts that would focus on. And then from there, they say f both these graphs, for you to get a negative, one must be above and the other below, or like this. So we can see that here on this side, f is above and g is below. So f is positive and f is positive and g is negative. So we have a negative this side. And then in between, if we check in between the x-intercepts, here in between the two x-intercepts, you can see also f is above, f is positive, g is negative there. And then that means we would have a negative here. And also, if we look at this side, the right-hand side, you can see that both the graphs here are below. So this would be positive. And we want where they are both negative. So this would be in between and also that side. So it should be x trapped between -4 and 0. And it should also be when x is less than -4. So that would be the solution for that. X is less than -4 and x is trapped in between -4 and 0. Alternatively, you can say it goes all the way that way but skips this. You can say alternatively x would be less than the smallest value there. The biggest value that you have here is 0. You can say x goes that way. So x is less than 0. But with the condition that x cannot be equals to what? -4. So all the values of x that are less than 0 except -4, that one will also be acceptable. Right, that is how you work with inequalities. Remember here, you need a lot of practice for you to get used to how this operates. Right, I'm moving on now to the last part of our lesson, that is the nature of roots graphically. So we'll take deliberations on the nature of roots using the graphical approach. Right, to start off, we are going to be looking at the graphs there. We say roots are non-real if the graph does not cut the x-axis. So it does not cut the x-axis, we say roots are non-real. Roots are real and equal. If roots are equal, then the graph forms a tangent with the x-axis. It's tangential to the x-axis. That is if the roots are real. But if roots are real and equal, that is when the discriminant is 0. But if the roots are real and unequal, then you see that you get this root and this root. They are real, but they are unequal. You get those roots. Remember, we are analyzing all these roots for when y is equal to 0. That is the analysis of all the roots. They are analyzed when y is equal to 0 there. Right, now let's look at the illustration here for determining the nature of roots. We are going to subject this to different lines, and then we are going to talk to how many roots does it have, and then we can also write down the value of the roots if possible. Let's check the first line. The first line is y is equal to -9. How many roots does it have? One root here. And what is that root? X is equal to 1. The value of that root is x is equal to 1 when y is -9. Let's look at another line. Let's look at this line. The line y equals -5. It cuts here and cuts there. So how many roots do we have here? 2 roots. What are they? X is equal to -1 or x is equal to 3. So those are the 2 roots when y is equal to -5. Moving on, let's see when y is equal to 0, we get this root and this root. That is where it is intersecting that line. So y is equal to 0, we get 2 roots, and then from there we have them as x equals -2 or x equals 4. Those are the 2 roots. So that is how now when we move a line, you can see, you can check how many roots the graph has, and you can write down the value of those roots if possible. Right. Now let us look at the method in which you can approach some of the questions in the nature of roots. Case one, if you have that your unknown is placed in the place of y, then we are going to be moving a line y is equals to p horizontally or vertically up and down, and then we are going to check what happens to the root. So the graph doesn't shift. We are just going to be moving a line vertically and checking the nature of the roots. And then alternatively, we can also have a case two. With the case two, the unknown is in the place of what? Of the y-intercept. So the y-intercept was -3. Now I replaced it with -k. In this case, we are going to shift the graph up and down depending on what the question is asking, and then we are going to trace the y-intercept as the graph shifts. But we do have an alternative method to case two where you will change it to a case one problem. It is possible to do that, right? And then the third one would be when you have now the unknown f of x plus m. If you have f of x plus m, now you are dealing with a horizontal translation. To get the horizontal translation here, we have to then look at x plus m is equals to 0. What is the transformation? X is equals to negative m. So the graph is shifted. We're going to be shifting the graph to the left depending on what the question requires. So here, good people, I am going to take you through some examples that would need for you to be able to solve these particular questions, but please make sure you practice, because with practice you get better, because these questions are of a high order. Right, let's check the first one. The function f of x is x squared minus 2x minus 3 sketched alongside. Determine graphically the values of k for which, remember, you don't use delta, the discriminant. You have to use the graph. Now, you can see here that where there was f of x in the original function, we are now putting k. So we have f of x equals k, which means we are moving a line y equals k, such that it will have equal roots, such that it will intersect the graph once. So where can we place the line so that it intersects the graph once? We can place the line at the turning point. So if we place the line at the turning point, it intersects the graph once. So that is where we have equal roots. So that is y is equal to k. But what is y here? Y here is -4, right? Y is -4. Y is equals to -4 when the line is placed there, which means that our k would be -4. So that is where the line should be for us to have what? To have equal roots. I hope that makes sense. And then now the second one, you can still see that y, we are moving a line y is equals to k also here, but we have to place it such that we do not have any roots, which means that the line must not touch any part of the graph. If you draw the line here, it does not touch. So any place below the turning point, you can see that the line will not touch the graph. So any place below the y-intercept, the turning point, I mean, the graph does not, the line does not intersect the graph. So you would say that it is when now the value of y is less than what? -4. But we know that y is equals to what? K. So we will have our solution being k is less than -4. So that would be the solution. The line, when the line is below what? Is below the turning point. Now, the last one here, still you can see the parameter k is placed where there was f. So you can see that here we are going to be talking to when it has two positive roots. So we are going to be looking at a region or a space in the graph, a point in the graph where the line intersects the graph on two places, but it has to intersect on two positive roots. So if you are to place this line anywhere here, you can see this root is negative, this root is positive. Even if you move it down, negative, positive. You move it down, negative here, positive there. And we are looking for two positive. If you place it on the y-intercept, you can see one root is 0, the other one is positive. But below the y-intercept, what do you see? Below the y-intercept and above the turning point, both the roots are positive. So both the roots are positive below the y-intercept and above the turning point. So that is where now k is trapped between what? Between -4 above the turning point and below the y-intercept. So k is trapped between -4 and -3. So that's where the graph contains two positive roots. Right, let's move on to the other part there now. Now, if you look at this type of an example now, k is no longer here. K has now replaced what? The y-intercept, which means that now we can move the graph. We can shift the graph. Or alternatively, we can change this problem to be a type 1 problem. We can actually transpose the k to the other side where we get x squared minus 2x. This would be equals to -k. And then because this needs to look like that, needs to look like f, we are going to then subtract 3 both sides. If we subtract 3, you can see that we have f of x is -k minus 3 because this whole thing here is f of x. So you are going to be moving a line y is equals to -k minus 3. So you avoid moving the graph, you move the line because you've manipulated that. So we want it where it has equal roots. Where do we put the line so that it intersects once? We put it on the turning point. When we put the line on the turning point, the line y is equals to -k, -3, like that, we get that the line intersects the graph only on one point. So the solution for C would be, we need that y at this point is -4. So -4 would be -k minus 3, which means that k would be equals to -3 plus 4, k would be equals to 1. That is the first one, k would be 1. Let's look at D. It has non-real roots. For it to have non-real roots, the line should be placed below. The line should be placed, the line y is equals to -k minus 3 should be placed below. So this would happen when y is less than -4. But y is -k minus 3, so it should be less than -4, which means that -k would be less than -1. K is greater than 1. So k should be greater than 1 for us to have what? Non-real roots. And then now for us to have two real but unequal roots. Two real but unequal roots. For us to have two real but unequal roots, it means that the graph must intersect, the line that we draw must intersect the graph twice. So if we place the line anywhere above the turning point, you can see that it intersects the graph twice. That's what we are interested in. We are not interested in the sign of those roots. We are just interested in the fact that it should cut the graph twice. So it does that when the line is above what? It is above the turning point, the minima. So it happens when y is greater than -4. That means that -k minus 3 is greater than -4. -k is greater than -1. And then we get that k is less than 1. So that is where the graph now would be having two real but unequal roots like that. Right, we move on just to the last problem to wrap up our lesson for today. I had an activity for you I had an activity for you to do, but because of time, I am going to take you through what you had to do with that activity. With the activity, you are then looking at this particular transformation. You are no longer looking at a line that you move up and down. You are now shifting the graph to the left and to the right. So that is what is important that we are going to be doing here. Now, when we shift the graph, what is important to note here is that you need to check what the question demands. So we want two positive roots. If you check this graph, when x is equals to, you see here, this is f of x minus p is 0. So this is the line y equals 0, and then we want to move with respect to the line y equals 0, we want to move the graph such that we get two positive roots. Here you can see that this one is negative and this one is positive. So we want to move this graph like this, so that at least this point gets there, so that the graph now contains what? Two positive roots. So we have to move the graph that way for it to contain two positive roots. But the question is by how many units? So what we're going to do here is we are going to take it this way. We're going to look at the transformation. What is the transformation in this case? The transformation is x minus p is equals to 0, x equals p. So this means that we move f p units to the right. It has to shift to the right. So we know the graph would be shifting to the right. So now we want to know by how many units. So it's p units for now. So in order for it to shift to the right, if I can go 1 unit, because it's negative 1 and 0, if I can go 1 unit, I would put the graph on the x-axis, on the origin. Then if I move it just above 1 unit, then you'll get that the graph now is going to be actually is going to get two positive roots. So it is when x, or rather when p is greater than what? Is greater than 1. When you can move it just above 1 unit to the right, just above 1 unit to the right, you'll get that the graph will give you what? Two positive roots. So now we were moving horizontally. So it's important with the nature of roots using the graphical approach, you can move a line or move a graph, or you can move a line up or down, or move a graph up or down, or you can actually move the graph horizontally to the right and to the left and to the right. So you need to be very, very careful about that. Those are nature of root questions. They need you to practice and practice hard. Right, good people. I think we've come to the end of our lesson for today. I just need to take you through the summary, and then from there we'll conclude today's lesson. So very, very important, as I indicated, nature of the roots. You can move the line up or down, or you can move the graph up or down depending on what the question demands, or you can also move horizontally to the left and also to the right. That's very, very important. Right, now let's look at the summary and then conclude our lesson for today. Right, the learner can be able to, you can be able to determine the x and y intercept and write down the equation of the asymptotes. You have to be able to determine the equations of different functions if they are sketched for you. That's the first thing that we did. You need to be able to look at horizontal, vertical, and diagonal lengths. That was the first activity that you did today. You need to be able to apply the concept of transformations. We did transformations. I showed you the different types of transformations. I did with you the translation. Translation can be to the right or to the left or up and down. It can be horizontal or vertical. And then we looked at the reflection, which can be to the with respect to the x-axis or the y-axis, and then we looked at the horizontal stretch and the horizontal squash there. And then we should be able to solve inequality problems. I did explain the solitary functions, the comparisons, the combinations, and then I gave you an activity of which you worked with, and then we did corrections, and then solving nature of the roots graphically. I did show you the illustration of what it means to have the nature of roots there and how to solve them graphically. I showed you an example with case 1 type problem, case 2 type problem, as well as case 3 type problem. Good people, we've come to the end of our lesson for today. Please make sure that you practice as much as you can. Next week, do tune in. We'll be looking at inverses. So please practice and practice. Take care of yourselves and take care of each other and practice mathematics. Goodbye.